Hi, my name is Seyed Ghaffar. I am an associate professor at Brunel University, London, and I'm delighted to give this presentation on one of my recent research projects that came to an end regarding the sustainable bio-based building materials, and I hope that you enjoy the presentation. So the title of my presentation is High Performance Compressed Straw Board Materials. This was a nationally funded project from EPSRC, Engineering and Physical Sciences Research Council. It lasted for 2 years, and today I will be briefly talking about the results of this project. I would like to start by saying that my project was in line with the 17 Sustainable Development Goals set by the United Nations back in 2015. These are a set of 17 goals to transform the world and achieve the full sustainability. And specifically, my project focused on goals number 11, sustainable cities and communities, and goal number 12, responsible consumption and production. So we wanted to valorize agricultural waste. These waste materials are produced every year throughout the world. Once the grain is harvested for food production and whatever, the rest of the straw stem gets incinerated or burnt on the fields, and this contributes a lot to the CO2 emissions, which is a negative impact on the environment. What we have proposed with this project, we wanted to make a sustainable, high-performing building material instead of burning them or sending these agricultural waste to landfill. So that's exactly in line with sustainable cities and communities and responsible consumption and production of our resources. I would like to also give you some facts about the construction sector. 47% of all the UK CO2 emissions are linked to construction and operation of the built environment. So this is a huge number, and this is only obviously specific to the United Kingdom, but these figures are more or less similar in all the other big countries around the world, and in some cases they are even higher. Moreover, the construction industry generates about 35% of waste to landfill across the globe. This figure obviously is for 2009, so it's really outdated, but this just gives you some of the motivations that we have had in order to think about this project and try to deviate some of these landfill sort of waste and try to make some value, give them some value in order to be able to produce building products using agricultural waste. So the concept summary of this project was that we wanted to come up with an improved lightweight variant of CSB, which stands for compressed straw board. The point of lightweight was extremely important, so our industry has already produced products from bio-based resources such as medium density fiberboard (MDF), which has a density of 750 kilogram per meter cube. But for the CSB, we wanted to make it a lot more lighter. So the compressed straw board had a density of 500 kilogram per meter cube. So it was quite lighter than the, let's say, competitor medium density fiberboards. And we wanted to obviously introduce this product to the construction industry. Therefore, it had to be strong enough to accommodate structural loads, both in tension and under compression. The project was also exploiting a novel concept of industrially efficient and highly selective removal of defects in the straw raw materials. I will explain what these defects are in the future slides. We wanted to use a method which is scalable and it can be implemented and it can be feasible for industrial scale, large scale production of these materials. And the optimizing of the straw feedstock, i.e., removing its defects, parts of the wheat straw that cannot take the load as much as the other parts, so therefore they are a defect. They had to be removed. Another point was that we wanted to improve the surface of these straw materials so that they can create a better bonding when they are compressed together using high temperatures and high pressures. And if we focus on these two factors, two important points, so removing the defects and improving the surface chemistry, we will be able to enhance and improve the mechanical performance of compressed straw board, as well as the physical performance, durability, water absorption, and the sort of other durability factors, the moisture content and all of that, which are extremely important when it comes to introducing a product to the market. So this represents the concept diagram of the project, HPCSB, High Performance Compressor Straw Board. It starts from here, so we wanted to focus on modular systems. These compressed straw boards are coming in a modular form and they just get assembled on site to have a low-rise building, a farmhouse, and other similar projects. We had a partner called SpaceLink Trust. They were giving us sort of these foundations and these wall elements that we could use in order to fit our CSBs. Main focus was on raw material optimization, defect separation. So you are looking at the raw materials here in this picture, and we wanted to remove all the defects that we find in this straw, wheat straw specifically. And another work package was to integrate the compressed straw board into the SpaceLink system. We had to focus on the pre-treatment of the material in order to enhance their properties. We wanted to come up with the environmentally friendly manufacturing methodology. So we didn't want to use high energy intensive pre-treatments or chemical agents to optimize and improve the raw materials. We wanted to just use a very mild a combination of physical treatments to improve the surface chemistry. And most of the project, of course, in these type of product development project is about testing and validation of the hypothesis, of the results, and ensuring that they are up to a certain standard to be able to be used in the built environment sector. So it starts all from the coordination and communication. We had two project partners, including myself as a principal investigator. The project was defined using 4 different work packages, starting from work package 1, raw material characterization and pretreatment, feeding that information into selective processing for optimization of the raw materials, then moving on to the manufacturing process for the development of prototypes. Work package 4 was all about testing, characterization, and impact evaluation. So in terms of the life cycle analysis and life cycle cost, in order to be able to industrially upscale and write an appraisal for upscaling of this process and this project. So this is the picture showing the raw materials of the straw. This is the anatomy of the wheat straw stem. So these are the grains. Then you have internodes, then you have nodes, which basically acts as joints of these columns, let's say, of these internodes, and so on and so forth. So we have these nodes as defects because they are not good in tension. And I will show you their morphology in the next slide. So this was the raw materials that we were dealing with. And of course, on the surface, we had a lot of wax, a lot of silica, which makes the surface hydrophobic and does not allow any resin to penetrate inside the surface and improve the bonding performance of these raw materials. So we had to remove these silicon and these waxes on the surface of straw using an eco-friendly pretreatment. So this is the microstructure of the node in the wheat straw as is cut longitudinally. And you can see how the cross-section looks when you go from the bottom to the root, to the direction of the root, from the root to the grain head. So you have the cross section at this part, and you can see it changes, it becomes very compact, and then it enters the upper internode. These are some more optical microscopy and scanning electron microscopy images of the node. So in order to have the valorization pathways biorefinery, we had to identify which part of the straw is good for which application. So the internode, we focused on pulp production for the paper, and then you can make biocomposite out of internode if you compress them together. You can make energy pellets for incineration, anaerobic digestion for the production of biogas. You can then use enzymatic hydrolysis for the production of bioethanol and production of bioplastics. But for the node, because it has high content of wax and lignin, you can extract the wax and lignin for aromatic compounds, and wax can be used for coatings, flavorings, food supplements, cholesterol reducing agents, and cosmetic purposes. So each part of the wheat straw can have its own valorization or biorefinery pathway. So I looked at in the context of biocomposite, this project was, essentially developing a composite for the built environment. We looked at the tensile strength. This was very important for us. So the tensile strength of the internode and node, you can see there is a huge difference between the tensile strength of the internode and node for the case of untreated straw. So as received, as harvested from the farm, the internode tensile strength is around 66 MPa, whereas the node is only 12.4. So node is not designed in a way to be able to sustain any tension. So that's why it is a defect. It could be a defect in the context of a biocomposite. We came up with a treatment which I called it H plus S, is essentially 30 minutes of hot water washing plus 30 minutes of a steam pre-treatment for the straw. And you can see that substantially improved the tensile strength of both node and internode from 66 to 88.9 MPa for the case of internode, and for the case of node from 12.4 MPa to 20 MPa. And I did the separate effects. I studied the separate effects of hot water washing for half an hour on the tensile strength and the steam. And you can see most of the contribution to the high tensile strength is coming from the hot water treatment of 0.5 hours. When you look at the microstructure of the internode in tension, you can see that they have these long microfibrils that are very strong in tension, whereas for the case of node, it's not very good in tension because their microstructure is completely different to that of internode. Then we looked at the comparison of different bonding scenarios, inner to inner surface of the wheat straw, inner to outer surface, outer to outer, inner to inner for the untreated straw, inner to outer and outer to outer. And you can see that the best performance comes from the inner to inner connection of the hot water followed by steam pretreatment of the internode, around 5 MPa of single joint lap shear in tension. So this is the microstructure study of what happens in the when individual straws internodes are connected to each other and then pulled apart. In the case of untreated straw, we can see that we have as soon as we have some tension, some nucleation of microcracks, that is then translated to delamination at interface and separation and very low strength. Whereas when we have hot water followed by steam pretreatment, we have a very strongly bonded interface. Another important point about the steam treatment is the expansion of parenchyma, or let's say the microstructure of the straw, which allows the deeper penetration of the resin into the system, therefore making it stiffer and making it stronger, therefore contributing to a higher performing compressed straw board. So this is just some of the list of publications that came out from this study. It only involves from 2013 to 2020. After that year, in the past few, let's say 2, 3 years, we have published more data on this research. But mainly, most of the original contribution, is about the eco-friendly pretreatment, enhancing the tensile strength of biocomposites, understanding the characteristics of biocomposites, and how we should design a pretreatment tailor-made for a specific part of the bead straw. So as I showed you, we have internode and node. Each of these anatomical sections of the bead straw have a specific characteristics, chemical characteristics, physical characteristics, and mechanical properties. So when we are thinking about a biorefinery, we have to be specific and according to these characteristics, define an application with these parts. And we found during our study since 2013 that for biocomposite production is best to use only the internodes and not nodes because they are a defect, especially when they have very weak tensile strength. So if you are more interested in this topic or in the development of these bio-based building products that are extremely useful for the built environment, you can read all of these related uh, publications, and hopefully you will find it interesting. Essentially, we wanted to work and valorize with a waste, agricultural waste that every year the farmers burned and contributed to the CO2 emissions in the built environment and in the whole globe. And we are now finding ways in order to use them in a separate industry, in a construction industry, in a built environment for low-rise buildings, farmhouses, and so on. So thank you very much for your attention, and I hope that you enjoyed this presentation. Just some acknowledgements. So the funding that we received was from the EPSRC. The project partners were two small and medium enterprises in the United Kingdom, a Startlink System and EcoSmacLean. So thank you very much for your attention. And please do get in touch if you have any interesting questions, and we can have a conversations around potential future collaborations on this research. Thank you.